All right, welcome everybody to the December edition of the Amateur Astronomers Association of Princeton meeting, and it's so great to have everybody again meeting through our virtual connections, and with the idea that someday we'll get back to the campus of Princeton. We will carry on and keep the flame lit. And so our agenda tonight is on the screen here, and I just have a couple of announcements and actually a couple of things that I want to share with you as well as announcements. And then without too much time elapsing, we'll hand it over to Victor, who will introduce our speaker for the night. And our speaker will go as long as she may like. I think typically an hour, but maybe a little over is totally fine. After that, and after the question and answers, we'll take a 5-minute break, and we'll come back and we have some fun astronomy by and for members in store for you, including Surabhi is going to give us the Unjournal Club tonight, her Iceland adventure, which I understand does include the Aurora. So stay tuned for that. We're going to take some time to get more into some new initiatives. I'll mention those up front here, but we're going to have time after the break to discuss them in a little more detail, as well as the proposal that I want to discuss with you guys to see if we have any takers to revive the Astro Video Live sessions for this winter. So this is on my mind, and I'm sure all of your minds. And in fact, 1 week from tomorrow, fingers crossed, knock on wood, if all goes well, the long anticipated James Webb Telescope launch is scheduled to take place. And this really is something out of sci-fi. And I don't want to steal any thunder from our speaker tonight, who has some expertise in this whole area of space telescopes. But I do think that as AAAP members, every one of you should be glued to your television or your computer or some video app to tune into the launch, which interestingly enough, is not taking place down at Cape Canaveral, but instead at the French Guiana Ariane 5 launch site. The SA had collaborated and contracted with NASA many years ago to handle the launch aspects of this. So this will be a first for us. I'm actually not quite sure about how the video is going to go, but I'm certain there will be some way to access the launch of this. And it'll be a site that we've never seen before. And I know you guys have seen these images. They're all over the internet, the aspects of this that are so unique and unusual. The folding of the scope and getting it inside the enclosure of the launch vehicle itself is an engineering miracle. And if this thing can go according to plan, some months down the road, we're going to have a telescope mirror out there that is several times larger than the Hubble primary mirror, as you can see in the lower left there. So a lot of excitement about this. And, we can talk about it after the break if you like. I did want to let you know that the AAAP merchandise store that we've been talking about, member Rich Sherman did the work and the brain power behind this and has launched. We have launched the shop, and it can be accessed right now off of Sidereal Times. We're going to have the link embedded on the front page of the website, but for now, here is the current Sidereal Times, and you can access the link. Also, we are launching a social media platform called Discord. I sent an email around today to all the membership, and I know you guys, several of you have seen it. We've had about 20 people join in already. On the platform, the so-called server. So this is a unique thing for AAAP. We'll discuss this after the break more, but I did want everybody to be aware that it has launched, and go to your email earlier today before noon and find the email and some information about how to join our app using Discord. And then maybe the most exciting thing is that in the observing realm, I'm going to see if I can bring up my favorite astronomy program, sharing. Yes, sharing. Hang on, get this right. Yes. Can you guys see a little planetarium program here?
Yes.
Great. So this is the Sky 10 solar system app, a little applet within the program Sky 10 that we use for so many things out at the observatory and as our general go-to for finding objects in the sky. And the Planetary program I've set up here to show the approach of comet Leonard, which entered our solar system from, they think, the Kuiper Belt, although I don't think they can rule out that it might have been the Oort cloud, coming in on an elliptical orbit, discovered in January of this year by astronomers at Mount Lemmon out in Arizona, one of my very favorite places in the whole world. That discovery led to a lot of people paying attention to the approach of this comet coming into where just last week and the last several days, we've been able to get images of it here, right here in New Jersey. I'm going to click on the time function of the Sky 10, which lets us increment the movement of the solar system. I have the time increment set for 7 days, and basically, it's going to advance the motion of the elliptical orbit of the comet, and I'm going to bring it in close, and I'm going to stop it and show you another aspect of this that I think is worth sharing. So here comes the comet moving in. We're already in May, June, July, August, September, October, November, stop. And I'm going to go back 2 weeks to where we were, and I'm going to see if I can bring up the angle here and bring up the scale here so you can see what has happened. And now, okay, so the orbital elements that the Sky 10 is plotting to show this elliptical orbit are not quite accurately enough resolved to get the part of the ellipse where it comes around. So that looks a little artifactual there, but nonetheless, its position relative to the Earth is what I wanted to show you. And you can see the position. If we are here in the blue planet looking at the comet, you can see only 7 days ago, December 7, December 8, the morning of the images I'm going to show you next, the comet was in a line of sight in the morning, and you could see the comet just before the sun rose. And you can see that angular inclination, a direct morning view of the sunrise, and you could see how the comet would be very, very close to the sun. Indeed, as the days have progressed, even today now, it is lost in the sun, and you could not observe the comet from anywhere on Earth. In a few days, it's basically going to come back out the other side. If I just advance it by 1 week, you can see it's jumped from the right side of the sun angle to the left side, if you will, and that means it's going to become an evening object, and we'll be able to observe it above the western horizon at night. And now if I can stop sharing this, what I really wanted to show you was the wonderful work of some of our members, and let's see if I can get back to my slides here. Here we go. And showing, should see a black screen? Yes, that would be good. Yes. And here, member and Princeton faculty member Bob Vanderby has captured amazing detail. About a week and a half ago, December 3rd, I guess 2 weeks ago, December 3rd, Bob took his telescope out, I think at the Princeton battlefield. Bob, if I'm butchering how you actually did this, please mention it. But Bob has made a composite as the comet came very close in its position in the sky to the glorious Messier object M3, the globular cluster. Bob's telescope, of course, field of view couldn't bring them both in together, but what he's done is an overlay of separate images, but put together as a composite in their actual position relative to each other that morning of December 3. And Bob braved the cold with his portable setup and got this amazing image that I think just really brings out a lot of aspects of the size and the orientation of the comet. And then also member Tom Swords, using his portable rig, a small refractor and a ZWO video astronomy camera, captured these two images just last Thursday, December 9, really showing nicely the length of that tail and the gases being emitted and the colors, telling you about the complex chemistry of the sublimation of the gases from the core of that comet, and just a beautiful sight about an hour before sunrise. Maybe a little bit easier for me working from my home observatory, so I actually did have to go out and open the roof, but I was able to capture these images at a higher magnification using a much larger telescope, a 12.5-inch reflector, to capture the comet the very same morning. And you can see these features that I was just talking about, the really eerie glow of the nucleus of that comet and these layers of the bright gases that are coming out and the tail showing the reddish glow. Here, the field of view is about 38 by 25 minutes, so less than maybe 60% of the width of a full moon is the image, is the scale of the photographs you're looking at. So really a once in several years, maybe once in a decade comet here to see something come this close to Earth and present itself so well. Right now then, as we go forward, if you can get out the clear evenings after sunset, you're going to have a good view of the horizon. But I think this is going to be a binocular object for some time to come as we head into January and as it begins to basically leave the zone of the Earth. Has anybody seen it without a camera yet? Has any member on the meeting tonight been able to see this with your eyes?
Rex, I did with a 114 millimeter Newtonian. It was barely a smudge, and then we had some haze coming in. But yeah, I did know that it was there. I can't say that it was the easiest thing to actually observe, but I did know that there was a core. And then just today, I was driving on the Hillsborough bypass, and there's a high spot, and I stopped and I tried to look with binoculars, but I wasn't expecting to see it, and I didn't. So.
Well, so I think at this point, I'd like to stop my blathering and turn it over to Victor. And we have an interesting evening in store for us. So I have already stopped sharing. So it's over to you, Victor, and take it from here, please.
Tonight's featured speaker is Dr. Joleen Carlberg, who's STIS branch manager at the Space Telescope Science Institute. Her presentation is entitled The Fiery Fate of Exoplanets. What happens to planets when their stars begin to die? For many of the planets we've discovered outside our solar system, the answer is a trip into the fiery depths of their host star, particularly when that star becomes a red giant. In this talk, Dr. Carlberg will share her investigations into what we know or think we know about the physical changes a star undergoes during its lifetime and how we can use this knowledge to search for evidence of planetary engulfment. Dr. Carlberg earned a BS in astronomy and astrophysics at Villanova University and her MS and PhD in astronomy from the University of Virginia. She was a Vera Rubin postdoctoral fellow in astronomy at the Carnegie Institution of Washington and was a NASA postdoctoral program fellow. Currently, she supports users of HST's Space Telescope Imaging Spectrograph, the STIS. Her research interests include understanding the effects of stellar evolution on a star's planets and characterizing stellar properties using ultraviolet, optical, and infrared spectroscopy. Toward that end, she's been awarded substantial observing time on some of the world's premier telescopes, including HST. Dr. Carlberg is active in astronomy outreach, leading public observing sessions, presenting sessions at local schools, and conducting astronomy chats at the National Air and Space Museum. So with that, we welcome Dr. Carlberg and thank her for joining us tonight.
All right. Thank you very much for inviting me to talk to you today. I want to start off by showing you this artist's impression of exoplanets, planets that are orbiting other stars around a multitude of stars in our galaxy. And over the last several decades, we have learned so much about the great diversity of planets there are outside of our own solar system. All right, apologize for the delay. All right, so like I was saying, you're looking at an artist's rendition of many exoplanets around other stars. We know a lot about the diversity of these exoplanets, and it looks very different from our own solar system. So what I want to talk to you today is to start off with kind of a large overview on what we know about the diversity of exoplanets, and also give you some background on what we know about the common evolution of different types of stars. And what I hope to convince you is that of many exoplanets is indeed going to be fiery based on what we understand about these planets and what we understand about stellar evolution. And then I'll take you on a deeper dive, focusing on my research into red giant stars. Oh, am I sharing? Yes, okay, sorry. Into my own research in red giant stars and looking for evidence of this engulfment that we're pretty sure is taking place throughout the galaxy. Okay, so this plot here, this figure here is just showing how we tend to think about exoplanets. We're able to generally measure two key characteristics that give us a sense on what the environment and potentially the composition of these planets are. And these two things are both the size of the planet, which may either be a mass measurement or a radius measurement, depending on how that planet was discovered around a star, and then also to the distance of the star. So I'm showing a two-scale model of the planets in our own solar system. So as you're well aware, we have both gas giants and ice giants in our solar system, as well as a small amount of terrestrial-sized planets. The figure on this plot is showing an example comparison of our own solar system distances to an example Kepler 11 system. And I'll note that the scaling of the planet sizes are self-consistently scaled, and but on a different scale is the separation, which means that the large points are larger planets than the small points, but they're not in the same scaling as the separation. And what I hope is immediately clear to you, even in this one example, you can see how very different exoplanet systems may look compared to our own solar system. So Mercury, of course, is our closest planet to the sun, but in the Kepler 11 system, you have 5 planets all orbiting closer than our closest planet, and all of these planets are in fact much larger than Mercury is. In fact, these things are packed that they're at the dynamic stability of the system, which means if you try to move these things any closer together, or maybe made some of them more massive, the gravitational interactions between the planets would actually destabilize the system. And this is something I don't think astronomers really expected to see when we started looking for planets around stars. And now to take a much larger picture, I'm showing on this diagram our solar system planets with these large colored circles compared to the large number of known exoplanets as of a couple of years ago. Again, using these two key characteristics. On the left-hand axis is the mass of the planet, and on the bottom axis is the separation. And both of these axes are logarithmic, which means you're actually stepping by powers of 10 as you move along the axis. So just to orient you here, Jupiter up here is at 1 Jupiter mass. So anything above this one line, one horizontal line would be more massive than Jupiter, and things beneath are less massive. And this bottom axis is scaled to the Earth-Sun separation. So sitting here at 1 AU. So all of these planets interior to Earth are orbiting their star much closer than the Earth is. And I want to draw your attention to two populations here. The first, indicated by this box, is a sample that it turns out to be very common throughout our galaxy. So these are masses that are at least a few times more massive than our Earth, but are still significantly less massive than our ice giants. And so we have no example of planets in this mass range in our own solar system, but you can see by the density of points here that they're actually extremely common throughout the galaxy, which is really interesting. And so these planets sometimes called either super Earths or mini Neptunes to give a sense of their size. And their compositions are probably have a large diversity as well, ranging from the types of things on Earth to the types things that you see in the ice giants. The other thing that I want to highlight is within this population, very close planets, so these are all things closer to their stars than Mercury is, you see there's actually a lot of things that are extremely massive. So things at Jupiter mass 10 times, maybe even 20 times the mass of Jupiter, orbiting very close to their stars. And this population I find particularly interesting because they're large enough to have substantial reservoirs of, say, angular momentum, or they have significant amount of mass compared relative to other planets, still small compared to the star, but starting to get to a much larger fraction, which, as you'll see, will become very important. Okay, so that's my broad overview of what we know about exoplanets. So let me just step back and tell you a little bit about stars. So the plot that you're looking at here is a Hertzsprung-Russell diagram, which you'll see variations of this plot throughout the talk. On the left axis here is the brightness or luminosity of the star. Again, this is in logarithmic units. And on the bottom axis is color or temperature, which in these plots, I'm always plotting bluer or hotter things on the left and cooler or redder things on the right. And what you need to know is that stars don't live just anywhere on this diagram. When stars begin their life and begin fusing hydrogen to helium in their cores, they will fall somewhere along this diagonal that's called the main sequence. And where they fall in this plot is directly related to how massive they are. The more massive things fall up here, the less massive things fall on the bottom. So if you plot a main sequence on here, you right away know how massive it is. The giants and supergiants sit to the upper right in this plot, but it's harder to actually figure out what the masses of stars are, and I will show you why. So this, I will play this movie in 1 second, but I just want to that this is now the same plot, again, showing the luminosity on one axis, the temperature on the other. And this is plotting a model of a single population of stars that were all at the same time. When I hit play, what you'll see is the more massive stars evolve very quickly into these giant branch type stars. And it takes a lot longer for the less massive stars. However, once you start getting down to like the intermediate and lower mass stars, I'll let this play one more time. Hopefully what you'll notice is that these intermediate and less massive stars, they all tend to evolve through the same part of this diagram. So when you find stars on the red giant branch over in this region, you don't actually quite know very well what mass the star was that went through it, because lots of different masses will have the same temperature and brightnesses as they evolve along the red giant branch. Okay. And just to kind of help you think about red giants, I have here a 2-scale plot of some of the different sizes a red giant star will be. Now here, I'm specifically talking about the physical size of the star, and I want to remind you that all of these stars could have the same mass. In this particular example, they don't, but the sun will pass through all of these radius sizes. And so here's just some typical red giants that you can go out and look at nighttime with the naked eye: Pollux, Arcturus, and Aldebaran. But the really fun thing that you can do is that when you know the sizes of the red giants, you can actually go back to this plot of exoplanets and see where the radii of these stars fall relative to the separations of these exoplanets orbiting stars. So right here, I have this yellow box indicating where the sun's radius will be on this plot. And as I step through, you'll see when the sun in the future becomes a red giant, its radius will actually become so large that it's going to encompass the orbits of many of these exoplanets. And so you can assume that all of these exoplanets covered by the shaded boxes are orbiting at distances that it's inside the future radius of their stars. But it turns out it's actually even worse for planets. And that is due to the effects of tidal forces. Now, I'm going to show you a few cartoon examples here. And if you're trying to do this in your mind, just assume everything is rotating in these plots in a clockwise direction. Now, most folks are familiar with tides in terms of the tides that we have on Earth. So I'm just going to take a minute to a quick overview of how that works. So due to the gravitational pull of mostly the moon, but also the sun, the water essentially on Earth closer to the moon is feeling a stronger pull of gravity than that's on the other side of the planet. And since the ocean water is very fluid, it's able to form a kind of tidal bulge around Earth. It's an extremely exaggerated drawing I'm showing here. However, because both the Earth and the moon are moving, and because there's a lot of friction in how water moves, the tidal bulge doesn't actually line up with the Earth, a line drawn through the Earth and the moon. The Earth is rotating relatively quickly compared to how quickly the moon is going around the Earth. And so the tidal bulge tends to leave the position of the moon. And because of friction and how the water is moving over the surface, this introduces a torque into the system that can transfer angular momentum to the moon. And so we are actually slowly slowing down the Earth and slowly pushing the moon away by about 4 centimeters per year. Now, when you look at the case of a planet orbiting close to, say, a red giant star, the situation is similar but slightly reversed. And this is because red giant stars as a population tend to be extremely slow rotator, on the order of hundreds of days, but when they become very large, they'll rotate even slower. And a that is relatively close to a star has an orbital revolution that's more on the order of something like tens of days, which means that you have an analogous situation, except that this bulging of the star tends to lag behind the planet. And so now your torques are working to pull, to spin the star up to align it, which strains angular momentum from the orbit, which pulls the planet in. But then as the planet gets closer, this tidal bulge gets larger because the differential gravity across the star is stronger. And its orbital period shortens, and you actually tend to have a rapid in spiral once these forces become strong enough to take effect, such that planets, Jupiter-sized planets that are 5 times the stellar radius are going to be rapidly pulled into their star. All right, so how do you actually destroy the planet? There's 3 different physical processes that might be at play depending on where the planet is relative to the star, what the composition is, how dense it is, and things like that. One method of destruction is also related to tidal forces. This is called tidal disruption. And this is essentially where something gets close enough to a more massive body that the different gravity across it, this tidal force, overcomes the strength holding it together. And this is how you form rings around the giant planets of the solar system. Because once you get close enough to the planet, these small bodies aren't strong enough, they get pulled apart and they form these nice rings. For planets around stars, this is probably the fate of more rocky things like the Earth. For things with puffier atmospheres, you have to first worry about something that's called Roche lobe overflow. And this is something that we know happens quite often in stellar systems. So this image here in the middle is showing contours of a gravity potential. So essentially, if you're too close to the massive thing, gravity tends to pull you that way. Closer to the less massive thing, gravity pulls you that way. And you can imagine if you put the small thing close enough to the big thing, and it's very poofy, that the layers of the atmosphere might become more gravitationally attracted to the more massive body and start flowing off onto the star. If your planet manages to survive both of these and encounters the star, then you have to worry about things like ablation or vaporization, where essentially you're heating up the planet or have a friction between the atmosphere of the star and the planet that can help destroy it. And just as an example, I'm going to show you where some of these different limits are for types of planets around 2 different stars. Excuse me. So I'm showing a main sequence star here on the left and a very small red giant star, only about twice the size of the sun here on the you'll notice this kind of fuzzy mottled region is the convection zone of the red giant, which is very deep and not so deep on the main star. And so you can take a calculation for a Jupiter and calculate where the Roche lobe overflow point is. And so for Jupiter around our sun, that Roche lobe overflow would happen outside the sun. And this red giant star, it just barely happens before it encounters the surface of the star. So you can imagine that as this red giant star grows, a Jupiter will actually be able to encounter the star's surface before it actually Roche lobe overflows. Something like the Earth, much more compact. You have to worry more about this tidal disruption. And in both of these cases here, the tidal disruption point occurs once it becomes inside the star. For around the sun, it doesn't get very deep before this happens, whereas for a red giant star, you have to worry more about these ablation processes because it actually would have to go quite deep into the star before tidal destruction will take care of it for you. Now, part of the reason I wanted to highlight this is just to give you a sense that depending on where these destroyed, you do have the opportunity to completely obliterate the planet, and with this convection, mix the material of the planet potentially into the outer regions of the star. Okay, so I hope I've convinced you at this point that planet engulfment is indeed occurring throughout our galaxy. And so now for the fun part is, particularly for me, this is my area of interest in research, is to try to figure out what signs of engulfment there are. So the first one I want to talk about is the fact that seem to be missing around red giant stars. So I'm showing you here the same plot that I showed you earlier on, where I'm showing the distribution of the masses of the planets compared to how far away from their stars they are, but I've color coded the points differently. So here, the black plus signs are planets whose host stars are still main sequence stars. But these bright, colorful points are planets that are orbiting stars that have evolved off the main sequence and are at some level of red giant stage. You can use the surface gravity of the star as a proxy for how large it is. So the red colored points are smaller red giants and the blue colored points are larger red giants. And you can see there's a much smaller population of the innermost planets around these evolved stars, which is particularly interesting considering that the most popular ways of finding planets are more sensitive to planets that are close to the stars, which means that these planets are truly missing. And in the cases where we do find these close-in planets, they tend to around the smaller giants. And so this, I think, is telling us that we're seeing evidence that a lot of the closer in planets have already been engulfed in these systems. Now, another key piece of evidence is related to the rotation of the star. I mentioned before that red giants tend to be slow rotators, and this has to do simply with conservation of angular momentum. So if you have a star that's spinning and you make the star much larger, the rotation speed will reduce inversely by the square of how much the star grew, which means if your radius grows by a factor of 4, your rotation is going to slow by a factor of 16. The sun is already slow rotating. Its rotation period is about a month. And so once it becomes a red giant, its rotation speed is going to be quite slow. And if you have a planet that inspirals into the you can dump that angular momentum into the star and cause it to rotate relatively fast compared to similar stars of that size. The third signature I want to talk about is that of pollution. And this is related to the idea that the compositions of the things that you're engulfing is different from the composition of what you're dropping it into. So as a reminder, most stars, including our sun, the vast majority of what it's made of is hydrogen, with the next largest component being helium, and everything else on the periodic table is lumped into another kind of 1%-ish thing that astronomers like to call metals. Whereas if you look like Jupiter, it turns out it looks almost exactly the same. You still have mostly hydrogen, a good chunk of helium, and maybe a little bit larger fraction of everything else in the periodic table. If you fast forward all the way down to the Earth, the picture now looks entirely different. So now hydrogen and helium are lumped into this 2% other, and the vast majority of the components of the Earth are much heavier elements. And if you remember from early on the presentation, that first population of planets that I highlighted, the super Earth and mini, this is a region of research where I'm very excited to see where the next decades will take us, because I think there's the potential for there to be great diversity in the compositions of these planets that also have a relative amount of heft, so that if you drop their contents into a star and mix it up, you might have a chance of seeing some of the chemical abundance imprinted on the star from mixing the destroyed planet into the stellar envelope. But until we get there, there is actually another few elements, and one in particular that we can take advantage of. And this is because they are systematically destroyed in the interior of stars. So the plot that I'm showing here is showing a large swath of the periodic table with the atomic number shown on the bottom axis. And on the y-axis, I'm showing the logarithmic abundance of these different elements. So again, logarithmic, every time you step by 1, you're multiplying by a power of 10. So hydrogen and helium, the most common are up here. And you can see as you go down the periodic table, there's a general decrease in the relative abundances in the star. There's this up and down odd even effect due to how actually helium atoms are fused together to power the stars. But what's really noticeable here is the extremely low abundances of lithium and boron. And red giants in particular are extremely lithium poor. So now I'm showing a histogram of measured lithium abundances for a sample of red giant stars, again, where this lithium abundance is on a logarithmic scale. We think the sun started out with an abundance around 3.3, and this value we get from measuring the relative abundance of lithium to hydrogen in meteorites. And we can observe the solar photosphere abundance of lithium right now, which is substantially less. So it currently has depleted its lithium abundance by a factor of 150 already. And you notice that the peak of this distribution for red giants is already at about 1,000th the amount that was originally seen in the sun, which is very interesting. So Jupiter, for example, is roughly 1/1000th the mass of the sun. So you can imagine that once you get below this line, a Jupiter now has more lithium within it than a red giant star that has severely depleted its lithium abundance. And as a way to illustrate that, I'm showing now a bar graph of lithium abundances, again on this logarithmic scale, and choosing 3 representative abundances pulled from that histogram of what a red giant star may start with. And you can just calculate, if you take a planet like Jupiter, you assume its abundance is 3.3 because you haven't destroyed anything. You can calculate how much would a star have mixed all of that planet's lithium into the star. And you can add more planets, whoops, wrong way. You continue to add more planets to see how much you get. And if you add a lot of planetary material, it almost doesn't matter what you started with, your output abundance would be about the same. And now maybe you've noticed the key trouble here in terms of understanding lithium abundances in red giant stars, because you can say, well, if I observe this amount of lithium in a star, what does it mean? Because if you were star number 1, severely depleted your lithium, you would calculate that you had to have engulfed at least a Jupiter's mass worth of material to explain the lithium that you see. Second star don't need quite as much, and star number 3, it turns out it didn't need to engulf anything. It just happens that's how much lithium that star has. And so that leads me to an active area of research is how much lithium should a star have? Would you really need to do to be able to say, did this star engulf or not? And to explain this, I'm going to go over 3 different areas of research. The first one being a project that I worked on a couple of years ago, and then the other are 2 ongoing studies to illustrate how I'm working to try to understand the answer to this problem. And the first, this case study of trying to use a group of stars in a cluster to answer this question. All right, so this is a story that I love talking about. This is a really fun puzzle to work on, of a lithiumrich giant that was discovered in the cluster NGC 6819. So I have a nice image, optical image of the cluster up here. Now, the important thing to know about stars in clusters is we think that they essentially all formed at relatively the same time with relatively, the same initial composition. And remember from that earlier plot showing how the stars evolve, you know that how long a star stays on the main sequence depends on the mass of the star. And since you're taking a snapshot of the stellar evolution process, you also know that all of the red giants in a cluster are essentially the same mass. There's a slight variation from the bottom to the top of the red giant, but they're basically all the same mass. So what I'm showing here is another variation of that brightness color plot. So this is now the apparent V-band magnitude. So brighter things are up here, fainter things are down like it was before. And the B minus V color, so bluer, hotter things are still to the left and the cooler, redder things are to the right. The purple thin line is a model color isochrone, which basically says where we expect to find stars that belong to the cluster. Background or foreground stars should kind of scatter around this line. And colored points are red giant stars associated with the cluster. The arrow is highlighting the lithium-rich star, which has at least 40 times more lithium than all of the other giants in the cluster. And I also want to highlight 2 different pieces of the red giant branch. So the stars that are along this first diagonal, these are first descent red giant branch stars. So this is where the helium core is inert. The star has just left the main sequence, and it is slowly going to evolve upwards here until helium fusion ignites in the core. And when that happens, it drops back down here to the circled group. So these are red clump stars. Okay, so one of the other things that you need to know about lithium and why it's so low in red giant stars, you can find out by taking a look at the interior of the star. So here's a main sequence star, here's a red giant star. And during the main sequence lifetime, stars like the sun have a very relatively thin convection zone on the outside. There's a temperature gradient within the star, and so below a certain amount, which is below the convection zone, lithium is depleted. And you get a little mixing with the surface, and so that's why the sun can actually deplete some of its lithium, because there's a little bit of mixing into this hot region. And then below that, you have hotter regions of the star. You eventually place where nuclear fusion is happening, and you have a whole bunch of other things going on. When the star becomes a red giant, one of the key characteristics is that this convective envelope, which essentially think of it the bubble part of the star, it's like it's boiling. The amount of material that's boiling is very deep. So what that means is that any lithium that was at surface gets mixed deep into the star, into the regions where there's no lithium. And so you dilute the amount of lithium that you had left in the star. And you also, it turns out, dredge up some of the byproducts. So in particular, you actually change the ratio of carbon to nitrogen. And that's an important point because we can measure the relative abundances of carbon and nitrogen to confirm that this star didn't undergo dredge up. So we know the mixing that should have diluted lithium has happened. And so that's why it's so strange that this star has so much lithium. Now, based on the story I've been telling, the first thing you can do is say, hey, okay, well, let's figure out how much would you need to drop into a star to explain that lithium. It's a fairly easy calculation and it doesn't work out at all. It turns out you need to have 0.1 solar masses of material, which is the size of a star, not a planet. And we know the stars, particularly these low mass stars, they actually burn up their lithium much faster. So that doesn't work at all. Okay, so now what do we do? Well, there's another interesting observation about this star. That a paper back in 2011 questioned whether this star was part of the cluster. So now what I'm showing is, again, this V-band magnitude. And I'm going to talk a little bit later about what this delta nu parameter is. This is a measurement that comes from astroseismology. But for now, just all you need to know is this paper was demonstrating the tight relationship that you get between the V-band magnitude and this delta nu parameter, so that all of the red giants tend to follow along here, and you actually get this nice clean separation between the red clump stars. And then, hey, this one's an outlier, or maybe this isn't really a cluster member, and that was kind of it. But we decided to pursue a little bit further what the implications of this sort of off delta value was. And the reason for that is because other than that one measurement, there's a lot of evidence that says, no, this really is a member of this cluster. So for example, the proper motion. So this is the motion in the two-dimensional plane of the sky. It's a 90% likely member based on how all the other stars are moving. That dimension of motion you can get from the radial velocity of the star. So this is the towards or away from you motion. And so this is a plot from our paper showing the distribution of radial velocity of known cluster members. Our star of question sits right dead on in the middle. So it's moving exactly the way in three-dimensional space all the other ones are. We already demonstrated that it's here right where you would expect to see it for a red giant star that's at the distance. It has the right colors, it has the right brightness. And most conclusive of this came out 3 years after we published is that the Gaia parallax, which gives you an independent measure of the distance, also confirms that it's at the correct distance of the cluster. So there's a lot of evidence that says, no, this is in fact a member of the cluster. All right, so what is this delta nu parameter and what can we do with it? So I'm going to be now in a brief just overview of the field of astroseismology to give you a sense of how powerful it is for understanding red giant stars. So we tend to think of stars as these, relatively stable balls of gases. But in fact, there's a lot of motion involved with these stars. So you have, as I talked about before, there's the convective motion of the stars, but there's also large scale variations of the star that you can kind of think of as ringing motion in the star. So you have layers of the star that are moving outwards and inwards at various, in spherical geometry, you have various nodes all over the star. It's actually ringing with a very complex sound. And because you have regions of the star that are getting slightly larger and slightly smaller, this actually imprints as small variations in the brightness of the star. And thanks to some of these really world-class space instruments, the Kepler telescope and telescope, which measure very high precision light curves of these stars, you can take these and figure out what frequencies the stars are ringing at. So this plot here is showing just that. So this is where you took a light curve of the star and you transformed it to see what are the frequency modes that the star is ringing at. And you can really think of this with the music analogy. Most things don't have a pure tone. They have a ringing at a complex range of frequencies, and stars do as well. And so here you're looking at the oscillation frequency, nu, of 3 different red giant stars. And these red giant stars have a very characteristic set of frequencies that they ring at, indicated by these rough bell-shaped curves. And you very clearly see this is a higher log G star and a lower log G star. And you can very clearly see how this maximum frequency that the stars rings at scale with the surface gravity of the star. You can read right off this plot that this is a much lower surface gravity star than this upper one, because this nu max scales directly with surface gravity. There's another parameter, that delta nu parameter, which is a little harder to illustrate, so I'll just explain it a little bit. But within this forest of lines, there's a characteristic separation between some of these sharp frequency peaks, which is known as delta nu, the frequency separation. And that parameter, it turns out, scales with the average density of the star. So surface gravity and density both depend on mass and radius, but in different proportions. So if you can measure both these properties, delta nu and nu max, you can actually derive both the mass and the radius of the star with very high precision. And since the star is a member of an open cluster, we actually have an expectation for what the mass and radius should be. And so we expected the mass of the star to be almost double that of the sun, and the radius to be almost 9 times that of the sun. But if you take that delta nu value that led those original authors to say maybe this isn't a cluster member, if you use that together with the nu max, you actually find that the radius comes out pretty close to what you expect, but the mass is much lower by a full solar mass. And what's more interesting about this particular number is that a star that is 0.7 solar masses, if you remember again from the beginning, lower mass stars take longer to evolve. If you started at 0.7 masses, the universe isn't old enough for this to become a red giant. So if this is a red giant, its mass must have been bigger to begin with. And so the theory that we end up hypothesizing for the result of this is that this star did in fact engulf something, but in the process of engulfing the star, the outermost layers of the star were lost, leaving a much smaller, a much less massive star that turns out to be the same size, which originally confused me, but I did some research into that. It turns out that for a star with an inert helium core, what sets the radius of the star is actually how massive this core is. And so if you scoop off a whole layer, a whole chunk of the atmosphere, it turns out the star ends up being the same size, which is kind of bizarre, I think. But that's what the physics tells us. And it's actually such that you don't actually get fully down to the convective, you don't get down below the convection zone. And so everything that you would normally look at kind of the same. So you're still in the part that's well mixed. But now what this means is that you're mixing, if you engulfed a planet, destroyed it, mixed it into the convection zone, you're mixing it in much smaller, much less mass. So now we think the convective envelope mass, instead of being 1.4 solar masses, is now only 0.4. And so if we redo the calculation, it turns out you only need something, it's still a fairly massive object, but it's something that's planetary size to explain the in the star. Okay, so that was our one case study. Now for ongoing studies, one of the things that we're trying to do to get a better handle on how stars should have is to measure it in a sample with well-defined masses and rotational speeds. And this is something that I'm collaborating with another researcher, Jamie Taylor from University of Florida. And you may wonder why such a study hasn't really been done before. And part of it is due to what I mentioned before about how it's actually really difficult to pinpoint the mass of a star when it's a red giant. And it's really only due to the relatively recent astroseismic capabilities of the Kepler and TESS satellites that let us do this to high precision. So what we're doing is we're taking advantage of this collaboration between Kepler and Apogee. Apogee is the Apache Observatory Galactic Evolution Experiment. And they realized that there was great potential for astroseismology if you're able to put some of these data together. So the Apogee survey, and the instrument both have the same name. So the instrument produces infrared spectra of stars, and from that you can get the temperature and metallicity and surface gravity of the stars. And Kepler, of course, gives us light curves, and if you can measure the oscillation properties, you can get the mass and the radius of the star to high precision. And the astroseismologists, of which I'm not one, so this part I find a little bit trickier, they can also distinguish between red giants that have this inert helium core, so a first descent red giant, and those that have a helium burning core. So this plot here is just showing one way that we could go about selecting stars. We basically focus on a narrow temperature range because that helps us get very precise abundances. And we're trying to basically measure lithium abundances of stars of different masses to see how much intrinsic variation there is. Now, despite that data, we still need to get more data to actually measure lithium. And the reason is that you get abundances of elements in stars by looking at the light that they absorb as the light is leaving and passing through the coolest layers of the atmosphere. Different elements and molecules will absorb light at very characteristic wavelengths. And one of the most lines of lithium is in the optical. And so we went and got additional data for these stars using the Subaru telescope, getting optical spectra. And what I'm showing here, 2 different red giant stars zoomed in on a very, very, very small range of wavelengths for color, where the lithium is known to absorb. And both the Y and the X axes are identical on this plot. And you can see, I think quite clearly, the lithium-rich star stands out in comparison to a star with much less lithium. So this lithium-rich star, the lithium absorption overpowers pretty much everything else here. Whereas in this star, there's a tiny amount of lithium absorption, but you can clearly see the presence of a neighboring iron line, for example, which is present here. You just can't really see it because the lithium line is so large. And so I can show you some preliminary results of how the lithium abundance, so again, this is in this logarithmic scale, varies with masses. So these 2 stars, just to help guide your eye, this is actually the most lithium-rich star we found so far in our sample. And from the Kepler, data, we know for the most part which stars are red clump stars; those are color-coded purple, versus the first descent red giant stars, which are color-coded in the light cyan. This is preliminary. We still haven't worked through all of our data. Actually, you're the first group I've shown this to outside of my collaboration, so that's pretty fun. So how do we interpret this? Well, the first thing you can do, my collaborator models of stars to see how much lithium you would expect to see as this dredge up happening, because you're destroying lithium at different rates. It depends on a lot of things that we don't quite understand. There's mixing, there's temperature gradients, there's all sorts of things. And so we have some models that predict this. And basically, we expect stars to fall within this gray region. And so the first thing that you can notice is that a lot of stars don't. We get about half the stars fall in here. Of the more massive stars, a lot of them actually have less lithium than we would expect. This is something that I've been plaguing our stellar evolution models for a while. We tend to underestimate just how much mixing happens in stars. So I think this is telling us that there's more mixing than we're really accounting for in stars. But the other thing to notice is that we do have some, substantially lithium-rich stars. And with the exception of this one unknown evolution state, they all, in this case, they are all red clump stars. So these are the stars that have already gone up the red giant branch once, which is interesting because that means they have already once become very large, which means they have had an opportunity to engulf planets very far out already before then shrinking back down to be a red clump star. And also interesting is that all of these tend to be, or most of these tend to be at the kind of lowest mass range of the stars that we've sampled. Now, I will highlight that the masses here, these are massive enough that they could have started at this mass and still be a red giant star in the lifetime of the universe. They aren't part of a cluster. We don't really have the handle that that we did before in that first case study to say what their mass should be. But it is kind of interesting that they do tend to a lower mass. And so this is highly suggestive of the kind of processes that I've been talking about. But of course, we need to process much more data, consider a lot more possible explanations before we can say with any certainty if that's what is in fact going on. Okay, and then the last ongoing study that I want to talk about is trying to connect all of these pieces together. So if you remember before, the 3 signatures of planet engulfment that I talked about is unusually fast rotation, this idea of pollution, a lot about lithium, but there could be potential other signatures of pollution, and the fact that red giant stars seem to be missing their innermost planets. The way that we're trying to tie all of this together is by doing a very detailed abundance analysis of a large group of red giant stars with different characteristics sort of connected to this problem. So we have red giant stars that have been searched for planets, and planets have been found. And we also have planets that are stars where we have searched for planets, but none have yet been found. Of course, this does not mean that they don't have planets, but they at least have a higher likelihood of not having planets at some random star where we haven't actually looked yet. And then we also have a number of stars in open clusters where we have measured the rotation speeds of these stars, picked out ones that show some enhanced rotation. Again, for open clusters, what you really have in your power is the fact that all of these stars all of the red giants should have evolved identically. So even a moderate amount of different rotation could be suggestive of engulfment. So the pollution signature that I'm working with another researcher at Space Telescope, Glenn Walgren. We're measuring lithium and actually a range of at least 16 different abundances, looking to see if there's any patterns of enrichment that might be suggestive of a relative enhancement that might look like an engulfed planet got mixed into the star, which is a very subject because we don't exactly know what the bulk compositions of these planets might be, but we have some thoughts on what specific abundance ratios might look like just on our kind of understanding of planet formation. And then the second piece of the puzzle has to do with really pinning down these masses, which, as you've heard, is really important for interpreting what we find. So for the stars that have been searched for planets, these tend to be stars that are not part of clusters. They're lone red giants. And so the masses are something that are really hard to pin down without astroseismology. And so I'm working right now with an undergraduate student at Howard University, Miles Pope, who is using public test data to do this light curve analysis to measure delta nu and nu max. And the question that we're most interested in asking is, are the masses of the stars where planets have been found, is that the same as the stars where no planets have yet been discovered? And again, this is a preliminary result where the stars with planets, the planet host pH, or these blue histograms, and the control stars, the ones that have been searched but nothing has yet been found, is orange. And there does seem to be, at least with our preliminary results, an offset here that the more massive planets are the ones where, yes, the more massive stars are the ones where we have found more of the planets compared to the lower mass stars. So this one is a very much a work in progress. So I unfortunately don't have any highlights to show you yet, but I'm really excited to see these projects moving along. And I think that in the future, there's going to be a lot more that we're going to be able to do because these stars are actually quite rare. And that's part of the problem with really trying to figure out what's normal and what is unusual and how unusual and where does it come from, is that these lithium-rich red giants are only a few % of all red giants that you see. But there's a lot of eyes in the skies right now for ongoing surveys, future surveys that are collecting a wide range of data that we can use to learn a lot more about what's normal for stars and help us to identify what's not. I haven't talked too much in detail, but one of those missions is the Gaia, which is measuring very precise parallaxes. So that's precise positions on the sky of millions of stars. And what you can use for that, use the parallax as the Earth goes around the sun. You can see how stars move relative to the background and get a very model independent measure of the distance of these stars. The TESS mission, you've heard me talk about, this is a essentially full sky high precision photometric survey. So we're getting lots of data on lots of different types of stars for which we can then measure astroseismic properties. And then these two telescopes here, the DuPont in the south and the SDSS 2.5 meter telescope in the these telescopes are used for the Sloan Digital Sky surveys, and Sloan Digital Sky survey number 5 is kind of kicking off now. The data that I showed you before, that Apple data came from Sloan Digital Sky surveys 3 and 4. So we're going to be getting a lot more red giant star spectra, which again we can then start better to this large wealth of data coming from other observatories. And I had to finish, of course, with a mention of the James Webb Space Telescope, as we all know, is launching in just over a week. And one of the big science goals for the James Webb Space Telescope is to get a better understanding on the composition of exoplanets. This is not my current field of research, but it's certainly a field that I watch with great interest because I'm really excited to see how much diversity we actually see when we can understand better what the compositions of these exoplanets are, particularly these super Earths and mini neptunes, which I'm hoping show some really interesting diversity. And so James Webb will actually be targeting some of the best candidates for doing detailed abundance measurements. It's called transit spectroscopy, where you essentially you measure the light of the star when the planet's in front of it and when the planet's not, and you subtract the two in a very complicated way. But it's the principle is quite simple. When you subtract the two spectra, you get residuals that are due to absorption of light through the planet's atmosphere as it left the star on its way to you. And so I'm really excited, and I hope you all tune in, as I will be next Wednesday for that launch. And with that, I will take any questions.
Okay, let's open the floor to questions. I mean, one basic question which I'll ask is, you've talked about a number of different things that you look at, fast rotating stars, well, a couple of other things. Can some of these indicators be used to identify candidates for looking for lithium enrichment, or is it the other way around?
Yeah, so that's okay. So one of the things that I didn't go to in great detail, just because it's a little bit circular, is how to interpret the abundance patterns of these other elements other than lithium. So I am using this rotation and this enhanced lithium as indicators of planet engulfment. I skidded over a couple of details. So there is the potential that you can regenerate lithium inside a star. It requires very specific conditions because you need temperatures that are so hot that you would expect to destroy it immediately. And so it has to happen in the presence of fast mixing to basically create lithium really fast and then move it somewhere else. So that is one of the, this is also why mass is so important. So that's another field is trying to understand if, when, and how that's happening. And one of the things that we're trying to separate out. So that's why lithium richness is an indicator, but not conclusive. Rotation is an indicator, but not conclusive. And so we're trying to find another piece of the puzzle that will help make be more conclusive. And so that's actually the goal of that last project is we're taking these things where we see enhanced rotation, we see enhanced lithium, and we're trying to look for, are there relative enhancements of any abundances that seem to stand out in the stars that we're saying, hey, these are candidates that don't seem to show up. Yeah, so that's the vision. I hope that makes sense.
On that exact point, can you clarify how you seized upon lithium in the first place? I mean, was it because the spectra were more identifiable and therefore you went in that direction, or what would you say to that?
So the reason is that if you know how much lithium the star should have, it is dead simple to see when there's too much. Right, so it's the fact that, particularly for these lithium poor stars, if you took a sample of stars where you know all of them should be lithium poor, and one of them isn't, then you say, aha, that is clearly something like planet engulfment has happened. So that was kind of the view that I had, but then as I was kind of working through this, modelers have been getting, like the stellar evolution models have been getting more advanced as well, and this is where there's some ideas of how you might be able to explain lithium through internal processes came about. Like I said, it's hard to do, it requires special conditions, but before that sort of complication and before showing that actually plausible to do it, it was because it would be a dead simple answer. But then the modelers told us that no, it's not dead simple.
I have a question is, our sun, how much lithium does that have? I mean, compared to the other stars, and is there any chance that our sun absorbed maybe a small planet back before, maybe billions of years ago, if that's the case?
Yeah, so lithium that we measure in the solar photosphere right now is 150 times smaller than what we measure from pristine objects in our solar system. So that's how we have a pretty good sense that we see lithium depletion already. The rate that the sun depletes its lithium, I think, is enough that if it engulfs stuff before, that lithium may have also been depleted. So there's some scale issues you have to be worried about. However, there is some really interesting research out there, which is been pioneered over the last, I think, a decade now at this point, by Jorge Melendez, who does ultra precise measurements of the sun compared to solar twins. And he has found some interesting abundance patterns that, and I don't want to say it backwards. I'm afraid to say it because I haven't read it recently. I forget if it's either that it's missing refractory elements. These are things that condense to rocks at relatively high temperatures. It's either missing refractories that I think suggest that they're locked up in our terrestrial planets, and that the last gasp of material that formed the sun pleated in those materials. But the idea is that you could also argue, particularly like for red giant stars, I didn't this explicitly, but what I'm hoping is that these super Earths, if they are very much more massive than Earth, but still have this refractory signature, right? So this is stuff, right? Earth is made of rocks. It's not really made of these gaseous things, things that tend to be gas at low temperatures, that you might be able to see a relative enhancement of these heavier, I shouldn't say they're usually heavier, but it's not a one-to-one relationship. It's the things that form solids at very high temperatures. You might see a relative enhancement of these things in red giant stars that engulf planets. So that's the hope. But the problem is that Jorge Melendez's work may be even more complicated, because he's arguing, no, you actually see the reverse of that pattern in the sun, because that stuff got locked up in the planets. And so now if you dump it black in, what do you actually expect to see? And then it starts to get a little bit circular, which is why it's a little bit of a fishing expedition, I will admit.
One question about, I guess, red giant stars in general, they greatly increase in size, which obviously means that their density, average density, is much less than it used to be.
Yes.
So I don't understand, given that, how are they able to maintain enough fusion to stay, to maintain that condition if they're so much less dense?
Because it's I don't know if I want to try sharing screen again. So the reason is that the low density, so in terms of mass, the vast majority of the mass is what's forming is contained, right? So it's boiling and mixing, and that's the stuff that's really expanding. So this is the weird thing with red giants. I still don't quite understand it, but when you have a shrinking inert core with a layer of active fusion, it causes the outer parts of the star to expand while the core is contracting. And so you kind of have like this weird kind of like double motion. And so you still have the fusion region, which is kind of way out there, but it's in the more dense regions of the star. You actually get a whole restructuring of the star once the core of the star begins fusing helium. Then the star kind of, the equilibrium, because the fusion is now in a much more concentrated region, the star actually collapses back down, because you don't have, because the pressure that's pushing it out is now deeper in the star than it was when there was just this sort of thin hydrogen shell going out. I hope I explained that well.
So there is a very large variation in density from the center to the edge.
Yes, and while it's going up the red giant branch, the core is actually getting denser and hotter, and will eventually get dense and hot enough that fusion reignites in the core. But while that's happening, the outermost regions of the star are getting more diffuse.
Okay, I've never seen in any book or paper or anything, a basic graph of density versus radius of stars, which is, I would have found very interesting, but it just never came across it.
Yeah, I don't know that. Okay. I think of a good one off the top of my head. I know I've looked at these values from reading in stellar models myself, but I actually can't recall if any of my basic astronomy textbooks had that plot either.
Could I add in a question there that I think really follows what Doug was asking on that? When you were talking about how there's evidence that red giants are losing their mass, and that lithium is involved in that process. How do you envision that loss of the mass? Is it just being dissipated from the low density outer regions of the red giant, or is there some event where it's being ejected in some fashion?
Yeah, so I will admit that is a little bit beyond my basic physics to say with any certainty. My vision of it, though, is that it would be a relatively short-lived event, and you can think about it as the fact that the outer layers of the star are the least gravitationally bound to the star. But I admit that I don't have a very good fundamental understanding of where that energy is deposited in the star. So I can only give a kind of hand-wavy explanation that since you have convection that has relatively fast time, that energy and angular momentum will get distributed.
Well, is it in any way related to planetary nebula that we observe in a general way? I mean, that in other words, that residual gas is still out there and bound in some fashion, but it's not part of the star anymore?
I think so. Like it would basically be an earlier of that type. What I would have to do is figure out, how much mass, how quickly it would dissipate. And there are some studies that have looked into this because there are some infrared excesses. This is actually another piece of the puzzle that is not well correlated enough to really say anything with certainty. But there is some suggestion that you do tend to see infrared excesses associated a little bit more with the rich stars, which then folds into that picture that you lost, like a more episodic loss of mass that is then expanding and cooling. And if you catch right time, you can see the infrared signature. But there hasn't been a lot of movement, honestly, in that field. I should probably figure out why. I think because in general, you expect that to be relatively short-lived, just like for planetary nebula, right? You need to look at a lot of stars for you to catch that happening. And so it might just be a probability game that you need a lot more stars and a lot more measurements before you can have enough data to say that with certainty. I'm speculating wildly at this point.
All right. Victor, you're muted again.
Sorry. How much does it tell you when you look at the light absorption from lithium in the outer atmosphere of a star about the overall lithium proportion in the overall star? What are the cautions that I don't know that you are worried about with how it mixes, for instance?
So this is one where what you see in what you're actually measuring, right, is just in the very, very edge of the. But since we know that the outer region of the star is convective, you can relatively safely, I'll just say safely. You can safely make the assumption that what you're measuring is representative because you're measuring part of that convective region. And I think the convective turnover timescales is only something like 100 days. So you would have to be super lucky to see some sort of enrichment in that outermost layer that isn't part of the rest of the star. And so you can basically assume that it's representative of at least the outer convection zone of the star.
A fascinating topic, and we wish you every best success in your future research and all the tools you get to play with the really big telescopes. We're totally envious of that. And we'll keep an eye on what's happening in your work and your publications. So thanks again for joining us tonight, AAAP.
All right, thank you.
Oh, good to see everyone. So today I'm going to recount all the splendors of Iceland that I experienced firsthand on a recent visit to this beautiful, ruggedly beautiful nation. So in late October, after receiving our booster shots, my younger daughter, she was getting a bit bored at home. So she suggested that we take a trip to an Instagrammable location. So after some research, she picked Iceland, and a guided trip was available on those dates that suited everyone. So come November 7, we are on our way. So I look out of the window and I see this strange faint glow. We were somewhere around, close to Iceland. So I didn't think that, I thought it should be pitch dark, but they appear to be northern lights. So I was excited, and I knew that this is why we were taking this trip to Iceland in November instead of going to some, nice warmer locale like Cancun or Costa Rica. So here is, I had my iPhone in my hand and I clicked some pictures. Of course, you see the reflection of the inside of the airplane, but this is what I captured from my iPhone. And all of you know how auroras are formed, how they happen, and they happen due to solar activity. So when energized particles from the sun slam into the Earth's upper atmosphere at speeds of, improbable speeds of like 45 million miles per hour. But the Earth's magnetic field saves us from these charged particles and redirects them to the North Pole or the South Pole, transforming this energy into this dramatic, dazzling phenomena. So a little bit about these lights that I learned was that Galileo Galilei was the one who coined this term, Aurora Borealis, in 1619, after the Roman goddess of dawn, Aurora, and the Greek god of north wind, Boreas. So people have been fascinated by this phenomena from the very beginning, and the earliest suspected record of the northern lights is in a 30,000-year-old cave painting in France. So at the beginning of last century, Norwegian scientist Christian Birkeland had proposed that the electrons emitted from sunspots produced the atmospheric light striking the Earth's magnetic field. And the sun, and we all know that the sunspots and sun's emissions go through an 11-year cycle. The peak activity of the last cycle was in 2014. And the next one is expected in 2025, and hopefully we'll all be there in Iceland. So at any time, the sun ejects charged particles from its corona, creating a constant solar wind. And when that wind hits the Earth's ionosphere, these auroras are born. And the bright colors that you see are from the chemical composition of the gases in the Earth's atmosphere. The green color that you see here is usually, it's associated with the oxygen molecules. And sometimes we see the red hue also, and that's the color radiated by the nitrogen. Auroras are best seen in the winter months, from November through February, because that's when the lights, the nights in that area are longer. So this was our first trip to watch. So we took an hour's drive. It was raining that day. So, our guide was trying to find a window, and, they have these watches where websites that they can figure out which area in Iceland is cloud-free. And then they take people, take the bus to that area. So we went south to an hour's drive from Reykjavik. And this is what we saw. It was very cloudy, raining, or now and then, but we were able to capture this little bit, as you see on the screen. So this was in Southern Ireland, south of Reykjavik. So we went another time, second attempt, and this time the skies were much clearer. It had rained earlier, but it was much clearer. And this was from a place called Thingvellir National Park. So at this time during this trip, the solar activity wasn't that great, but we were still able to see this much. So as you can see, there are always people, annoying people, who put their lights on. So we had these lights on for people, and our guide was continuously saying, kill the lights, kill the lights.
Mm.
But, people do what people do. So this was a 10-second exposure taken by my iPhone 12. And I thought it was pretty good. It was better than the guides. This is, another set of pictures. The sky was very pretty.
Did you have a tripod?
I did have a tripod, but we forgot to take it.
Surabhi, a question on your last image. Can you go back one? Yeah, is that a hill or is that dark clouds above the horizon?
Hills. Those are hills. And
Below the, just
yeah,
below the green, the line below the green, is that a mountain or is that the cloud?
Cloud. Yeah, those are clouds. The mountains are below. Can you see my mouse?
Yeah.
Yes.
Yeah. So these are the mountains, and it was just cloudy but near the horizon. But above that, we were able to see some lights, and this part was actually much clearer.
Yeah, cool.
That one.
Great portrait. I love it.
Yeah, I don't know. My eyes are fully open, but I wanted to. I wanted to tell you something about these. The geology of the island. So, Iceland sits right where on the two tectonic plates, where the two tectonic plates meet and are actually pulling apart. So this side is the North American plate on the left, and right side is the Eurasian plate. And what we see is the mid-Atlantic ridge in the middle. And all these tiny triangles, these are all volcanoes. So it looks as if, in a few million years, either Iceland will be a very big island or it'll be split into two islands, because the ridge is actually, slowly the plates are moving apart, they're drifting apart. So Iceland is, this is another figure that I found where you can see the mid-Atlantic range, with all the volcanic activity happening right here. And it's probably Iceland is probably the only place where the effects of two tectonic plates drifting apart can be observed above the sea level. We can actually see what is happening. So I'll show you some of the pictures that I took. This is of the ridge, where we had gone to see the ridge. And you can literally see the stresses on the land. And it's like you take a piece of cloth and you stretch it like this, and what you see are tiny folds forming on the cloth, and that's basically what we saw. And here I am walking on the middle portion where it is already moved apart. It was very cold. So the other thing that I wanted to show you is that besides these plates, there is a hotspot directly under the island, which also contributes to the volcanic activity. So so basically what these hotspots are, they're relatively stationary plumes of molten rock that breaks through the mantle and the crust on the surface. So what happens is these hotspots are formed over exceptionally hot regions in the mantle. That's the hot flowing layer of the Earth beneath the crust. And in those extra hot regions, the more buoyant rock, rises up through the mantle, and the crust forms a plume and erupts from the surface. So these rocks are so light, the lava rocks, that it's like holding paper. So I held one and I was so surprised. So this is at one of the museums we went to see, called Lava Museum. Then we visited a geothermal power station. Now 100% of Iceland's electricity is from renewables, 75 from hydro, 25 from geothermal. And the population is just 365,000. That's it. So from this, the spent water that is used, it is taken via pipes to the houses. And these are the water transportation pipes, and with wood in the mid here. And they don't lose any, they lose just about 1 degree in going up about 100 kilometers. The water loses just 1 degree. And that's because of these special pipes that they use. And this is one thing that I thought a lot of people would really like to know, is that carbon fixing. Carbon dioxide, this is a technology that Iceland has come up with. And because they have so much geothermal activity, the scientists decided to see how, if they can help in climate carbon fixing. And what they did was they tried, what they do is they push carbon dioxide mixed with water, like a soda fountain kind of thing, deep back into the earth. And and what it does, it creates, it releases the carbon, the calcium and magnesium, and then creates carbonates. And those carbonates they're solid rocks. They just remain there forever. So that's carbon fixing. That's really interesting. So this is how it happens. So water is used from the underground, used by the power stations, and then the carbon dioxide from after that process is again mixed into water and pumped back into the earth, forming these stable carbonate minerals. So this is one website that people can visit, if you are curious. The other thing that I saw was these large hothouses that produce, tomatoes there. And the problem with this is that, I mean, tomatoes are good and all, and it's nice to eat them, but these are not native. And they have then, they get the bees to pollinate, then they have aphids. Aphids are bad for the plants, so now they have imported white flies to kill the aphids. And then the worst part for astronomers is this, the lights that are used for photosynthesis, help in photosynthesis because it's dark for long periods of time. These are open to the sky. And we really, had annoying glow from one side of the sky because of these hothouses. So that's one thing that, somebody needs to tell the government that this is not a good idea. Then, of course, the flies, when they go out in the summer, they will have a negative effect on these horses and other wildlife. These are Icelandic horses. They look very morose though. So I don't know if you're interested, but this is the real geyser that I saw. This is the first time the term geyser was coined in, I think, 1294, when a powerful earthquake activated geothermal activity, and these hot springs were formed. And one of the, what we call as hot spring geyser was formed, and it was named geyser. So all the geysers now that we have are named after this original guy here. And there's another geyser, this place is full of geysers, and one of them is called Stroker, and this erupts every 8 to 10 minutes. And it's a beautiful sight. And then all around here, we found, spouts of steam like this. So these are all man-made steam vents. That is, and they actually release some pressure and prevent small earthquakes. So these pictures were taken from the bus. And the next slide that I'm showing you now is that we visited Black Sand Beach, and these are the two photographs of very beautiful and highly unusually long hexagonal basalt columns, and these are formed by cooling lava, and you can see that these are really massive. As you know, I'm standing in a cave on the other side of this hill. It's beautiful. So this was another cool thing that we saw. And then, of course, the Blue Lagoon. So all the spent water that is used in generating power, it's not lost. Some of it is transported to homes and hotels, and then they and the rest is here in these large man-made pools. And it's a great place for tourists to go and for a spa, afternoon of spa. And so we went there. And the other thing is that interesting, because I had seen it for the first time, was that the sun never rises above 30 degrees. That's where it remains. So it rises. This is probably 4 o'clock in the afternoon or so, but it's always there. So that was one interesting thing. And the place is full of waterfalls and whatnot. It's just lovely. This was one of the big churches in Reykjavik that we saw. And of course, what I didn't see was puffin. I really wanted to see the puffin, but it was late. So puffins usually come only during breeding season from spring through October or so, and then they go out to the sea following their favorite food, that's fish eels. So that's it. I do recommend people to go there because I'm ready to go there anytime. It was so beautiful, even though it was biting cold, and I had these toe and hand warmers, but still it was cold. Maybe in 2025, when the solar activities should again be at its peak, we can plan a trip as a club to Iceland, after the solar eclipse of 2024. That would be interesting trip. That is it. That's the end of it. So I had a great time.
Awesome.
Thank you. That's so cool. I have to say I'm feeling nostalgic looking at your pictures, because it was back in 2007 that we made our trip to Iceland, and I love that place. You're absolutely right. It's spectacular. Fire and ice. It's just,
Yeah.
it's nowhere like it. Yeah.
2025.
Yeah, I'll go back. Well, I know Dave was loving the geology there, so hey.
I was just going to ask Surabhi if she got to stand on the two different tectonic plates, one leg on one side and one on the other.
No, my legs are not that long.
I didn't think so.
Figuratively.
Figuratively, yes.
Yeah. So we did go from one side to the other.
Cool.
But it was real fun.
Well, you know, geology is a local form of astronomy. That's the way I like to look at it. So,
Oh, hey, I was just going to share just for a brief second a light pollution map of Iceland, if you didn't mind.
You mean non-light pollution?
Well, yeah. Let's see. Yeah, there you go.
yikes.
Yeah, I can work with that.
Yeah, especially
You're
out
not-
here.
Where do we put the observatory?
Yeah, there you go.
On the glacier.
Yeah.
As Surabhi
I
was
just-
saying, though, the hard part is getting a clear night.
Yes.
As opposed to, let's see.
Ground zero, red zone.
Here we go.
Oh, God.
Welcome to the
Yeah, so our,
United States.
Our observatory is, here we go.
West. There you go. Right in that
We're
orange.
right on the edge. We're right on the gradient.
Right
Right
about
on the
here.
gradient. Yep, right
Yep.
on the gradient.
Now, for those who talk about Cherry Springs, I'm going to show you a place where I went camping. My wife and I. Right, let's see, Cedar River Flow, right here. I don't know if you can see it, but there's a little peninsula that kind of sticks out. Look at the place where that is, black. Whoop.
Zoom out some more. Zoom out some more so we can see where it is. Yeah.
It's in the Adirondacks. So this is the Adirondack State Park, this circular area. And this is an area, this is Indian Lake right here. Is a very long, speaking of fault, it's when the Adirondacks got in place, the northocite got in place. And then later, as it cooled, there were a lot of fault lines that run northeast, southwest. And Indian Lake is one of them. There's another one over here, but this lake called Cedar River Flow, they used to dam it up and then they would let it loose so that they could run logs down down certain rivers. But that's in the
It's in
Adirondack
zone.
State Park. I don't want to take too much longer, but let's see here. Cherry Springs.
Dave, just
is-
a point there.
yeah.
The Adirondacks, I was there with the telescope. The problem is fog and haze moves in. So you're in
Yeah.
a dark spot, it defeats sort of the purpose for looking, in the sky.
Yeah. Well, it's just really, over the number of years I've been going there, it's probably, I don't notice much of a difference, but than anywhere else. But this is Cherry Springs, so this is more of a light blue area. So anyway,
Hey,
that's
I think we can dream about doing another field trip and sort of reviving the idea. We had made some attempts to get up to Cherry Springs a few years ago, and it's an idea we should keep on the table for a summer field trip, either the Adirondacks or Cherry Springs. Probably Cherry Springs would take less planning in the sense that just go with your scope. Adirondacks, you're going to have to deal with lodging preparation and stuff like that.
yeah, there is that.
But I love the idea, and we should keep it on the table because I think, I don't know about you guys, but I think I only have one life to lead. So